Okay, let's just start talk about the induction machines. Uh, the time the session I start to discussion about the transformers, we talk, actually I talk, about the war current between Edison and Tesla and how Tesla and actually the company Westinghouse won the war against the Edison in AC over DC. And I said one of the most component there was transformers because they have a generation in Niagara Falls and they want to transfer the power over 10 kilometers with few losses and they use the transformers there. But there was another also important component, again invented by the great Mr. Tesla, that helped the AC systems to grow very fast, and that was induction machines. And in fact, for a long time, we use them in most of the case as motors. So they are used in different form. In a single phase, you have it in your homes, your refrigerator, for example. In most of the cases, if it's not a very fancy one, it's using this kind of motors, at least single phase one. But three-phase induction motors are used very widely in industry. So if you are going to work in industry and one way or another comes to work with the electric motors, there is a high chance that they be an induction motors. They have used in large three-phase in pumps, fans, compressors, paper mills, etc. Everywhere you need a big machines, there are there because they are very stable and robust in many cases in comparison to the DC machines. But not all the discussion for the induction machines are for the past. Not everything is done by the Tesla and we are here just using. There are new discussions here. In the first session, I talked about the Tesla vehicles by Elon Musk. One of the advantages that they have, they are using induction motors inside the car for running the vehicles. So there are very new discussion even in academia about using this kind of machine, this kind of motor inside the vehicles, electric vehicles. While for a very long time they are known as a motor, not generator, like DC machine, they can both in both motor and generator mode. Nowadays they are used as a generator for a very famous source of energy, wind. In fact, most of the wind generators in the world nowadays use a kind of induction machines. And they are still under investigation. Myself has done my master and a good part of my PhD working on induction generators for the wind generators and all the problems that make us. So there are still also new ideas, new investigation into the induction machines and how they are transforming the world. The point I want to make that they have been used for a long time and that is not going to end soon. In fact, the application is increasing. But enough of that. If you look at the induction machines, it's not very much different, at least from the AC machines. So you will see in the stator at the outside, there are two kind of induction machines are shown here. We are going to discuss them. So at both of them, you see the stator, the larger part, which is by the name is static, is constant, is not rotating, and a rotor goes inside that, which is the rotating part. Very similar to DC machine. You cannot see a big difference here. The difference is that this machine is connected to the AC system, and we are going to talk about the three-phase. I'm not going to talk very much in detail about its construction and how its physics works, though it's very interesting. I just want to give you a very good understanding of the concept in the next few slides, that how is the principle of working this machine. Though it has a very interesting mathematics and modeling about the physics and how it really works. So, as I said, here you can see the stator and here you can see the rotor. And I said there are two kinds. This one is, we call it a squirrel cage. I know it's a funny name, but soon we will see why. Induction machine. And this one is called wound induction machine. The stator, if we have a cross section of the stator, it looks like this. You can see it here. And this is built by laminated high grade steel, so it's by lamination of high grade steel, and then a three-phase winding is put in a slots cut on the inner surface of the stator. What does it mean? It means you have three phase and you are going to put your windings somewhere like here. Or for the other phase, for example, a more realistic of how they really wound the stator, you can see it here. They put the wires inside those slots. I hope it's clear from where you are seeing that they put the wire inside the slot. And one thing you can see that the winding is somehow distributed for each phase. There are reasons for doing that. They want to have a better use of copper and iron. It's result in to have a better, improve MMF, magnetic motive force in the system, and it smooths out the torque, the developed torque at the end. So for your knowledge, we are not going to discuss very much about how they are distributed, these windings, though and electrical engineers, they should know better about that. But what you need to know that it's not just one windings there, they distributed in the space like that to have a smooth torque at the end. Then we have rotors. Rotors, as I show you, is inside the stator, and it seems very similar to what we have for the stator, though this time, and it has the same material. It's laminated ferromagnetic material. Ferromagnetic material, a good ferromagnetic material, because we want to low hysteresis losses. And we laminate it for low eddy current losses. And this time we put the windings in the outer slots that you can see. And there are two types of winding for this rotor. One is a square cage, and you can see it here. if you think it's not the best naming that they can use, I agree with you, but it reminds them somehow from for a squirrel cage, I believe. That's why they call it that. So here is the squirrel cage. Here we have these aluminum or copper bars that go through that slots that we have there. And then at the both ends, they are shortened by those rings. So it consists of aluminum or copper bars embedded in the rotor slots. So we talk about these bars. And are shortened at the both ends by aluminum or copper and rings. We talk about this. So they put this bar inside of the slot and then shorten it at both sides with help of these rings. Any question here? Yes, we put this bar inside of the slots, and then it's a rotor that I showed you previously. It goes inside the starter, this part that is moving. Any question? Okay. The other type is called wound type because instead of bars, they really use wires and windings there. So these times, instead of shorting the wires at the both ends, at one end we take them out and connect them to these two rings. We call these three. I'm talking about these ones and this one. We call them slip rings. Last time we have no control about the squirrel cage. We just during the building we can engineer it how is that. But after that we didn't have any access to rotor. But this time these slip rings give us access to the rotor circuit as well. They are like the input. So we can use some brush to connect them and fit them or add some resistance here. So here the terminals of the rotor winding are connected to 3 slip rings. And as I said, by using a stationary brushes pressing against the slip rings, the rotor terminals can be connected to an external circuit. But we talk about the brushes in DC machines, we usually don't like them. They are not very reliable. They have the problem of the maintenance. Usually the first place in the machine that is going to be faulty is slipping rings, because there's friction between them. You have stationary brushes that in slip rings that are moving. So they are the parts that are more likely to be faulty and need maintenance. So we don't like them very much. And there have been some quite works, even in recent years, that try to get rid of those brushes, some kind of brushless induction machines, that they didn't work that well, in fact, if you want to know. So the squirrel cage induction is simpler, more economical, and more rugged. But for your knowledge, all the famous wind generators using this type of the machine for the use. But for many cases of the motors, even when we need a control, we use them. And we are going to talk about them when we add resistance to the slipping rings, how it impacts the system. Any question here? Okay. If you have no question, everyone is done writing? More robust. There are less problem with the operation. They need much less operation in many cases. Okay, can I go to the next slide?
Do you use the same thing in a drill bit too?
Pardon?
Electronic drill press. Do you use the same systems too?
With the DC machine, you mean?
Yeah.
The DC machine, in basic, they are very similar, but they're not the same. The problem is that there we have a commutator. We have one stop the windings and one commutator. But here we have 3 slip rings and 3 brushes. In many cases, you don't use them. Try to just simply shorten them. But in the DC machines, there are no escape from them, and it's not just 3 of them. In fact, there are 2 brushes, but there are lots of circuit and windings that go through that commutator. So this one still is more robust than the DC machine, if you ask. But you are right. There are very basic, from the very fundamental and conceptual part, they are very similar. Okay, as I said, how really the flux and magnetic fields go through the circuit is a bit complicated. It's really interesting. If you are interested in the math and all of those stuff, I encourage you to read, but I have no intention to go to all the depths here for you. So in next year's slide, I just want to give the feeling and understanding of the very much basic of how induction machine works, why we call it induction, in fact, and we just want to get the very much basic. Because of that, we are going to lose some accuracy in my speak. I try to be very plain, but I try to convey the spirit to you, to get the very much concept of how they works. So first of all is a three-phase. So we have three-phase current here. One is here, IA, here is IB, and here is IC. So I told you that the windings are distributed in the system, but for the sake of simplicity, we consider the very simple concentrated winding. You see, there is just one winding, a very simple one. And we also consider two poles. You see, for each phase, we will see two poles. So it's the simplest thing that we can discuss about the induction machine. So we have three phases, IA, IB, and IC, and these three are shown here. You are familiar with the concept of three-phase voltage and current. So here is IA, here is IB, and here is IC. You can see them. And if I want to write them in a more mathematical way, you're already familiar with that IA is equal to IM, some maximum current, cosine omega t. IB is IM cosine omega st minus 2p third, and IC is equal to IM cosine omega st plus 2p third. It is also obvious from the graphs and curves you can see there are 200 degrees apart. So in temporal axis, in temporal space, there are apart from of each other 100 degrees, sorry. But if you also look at the poles there, the poles also, the windings in a spatial space, in a spatial axis, also are different, are apart from each other 120 degrees. Consider the pole here. And consider the pole here. So from temporal axis, the currents are 120 degrees apart. In the spatial axis, the windings are also placed 100 degrees apart inside the motor or machine in more general case. We want to see, so each of these windings will generate some MMF. But what we are interested in is resultant MMF in the air gap. How that resultant MMF will change inside the MMF by time going on. So we consider 6 instants of time and see what will be the maximum of resultant MMF in each time. So here we are at the time 1. So we are at the time 1. So IA is plus 10, IB and IC is minus 5. You can see it here, the current direction here is 10 like this, here is 5 like this, and here is 5 like this. Then the resultant MMF, and as a result flux, it will be like this. The maximum will be this vertical to the up. If we go to the instant 2, which is here, means IA and IB, each of them is positive 5. And IC is minus 10. Oh, sorry. Like 10 ampere. Then the flux will be in this direction. The resultant MMF will be in this new direction. If we go to instant 3, we come to the new point. It's like that our MMF, our field, is rotating inside the induction machine. In fact, if we want to visualize what is happening, it's very much similar to having a magnet like this and rotating this magnet inside the air gap. Pardon? Oh no, I just take 6 stands of the currents and try to find the MMF in each of them. See how the MMF, flux, will change, magnetic field will change in each of them. I want just to show you in each of these 6 stands. You can choose any other instance from this time current. So in fact, here is omega t, omega st. So it's the time. We go in the time to see what's happening. And if we continue going to the new point, for example here, now it will rotate and will be in this direction. And continuing, what we have a rotating magnetic field. If we want to be very accurate for you, in fact, we have produced some waves that are moving in a circle direction. But let's make it simple here. We have a rotating magnetic field. The magnetic field is rotating. Just remember the example of having a magnet that is moving inside the air gap. It's very much the same impact will be produced. And here is instant 6, which is here, and we are here. So if we go to instant 7, which means we are back in instant 1, the flux will return back to the first direction I show you. So the resultant MMF makes one revolve in a two-pole system. I should emphasize two-pole. In a two-pole system, the magnetic fields revolve one time in one current, one cycle of current. In one cycle of current, the magnetic field revolves one in a two-pole machine. So result of this three-phase induction is a stator will be a rotating magnetic field inside the air gap. But this go through the rotor fields. The maximum of this magnetic field is constant, but the direction is changing. It means the flux is always changing. The vector, the direction is changing, it means it's changing. Pardon?
When it's turned, it's work.
They just work, what do you mean? Energy?
Yeah.
We are getting to that very soon.
So, assume what's using a microprocessor.
We are getting to that very soon. Just save it completely for a few seconds. So this flux is rotating, it is changing. What we have from the Faraday law, E is equal to n d phi over dt. The flux is changing. So it will be induced voltage and current inside the rotor. That's why we call it an induction machine, because it induces voltage and current inside the rotor. But what Lenz's law told us? Do anyone remember Lenz's law? Lenz's law? Lenz's law was saying that the current is induced in a way that tries to reduce the effect of change of the flux. So if the rotor starts moving at the same speed with the magnetic field, the relative speed will be zero. We will have no change in the magnetic field. So by Lenz's law, this induced voltage forces the rotor to move, to reduce the relative speed, to reduce the change in the flux, in the magnetic field changes. So it starts to move. But it never reaches that speed of the magnetic field. Because if it reaches that speed, the relative speed will be zero. No voltage and current will be induced inside the rotor anymore. No torque can be developed. So it stays very close to the speed of the magnetic field, a bit short and shy of that synchronous speed, of that speed of the rotating field. And that's how induction motor works. And they are robust, because consider it, there are no two windings if you consider a squirrel cage. You don't need any brushes for a squirrel cage, no second supply, and it works very well. Not even a permanent magnet, anything. It just works based on induction. That's why we like it very much in the industry. Any question here? No question? Okay, I think we can take a break for 10 minutes and we come back after that. And we can continue from where we have left. So we just discussed what is the principle of induction motors, and I told you that we never reach, or let's say in 95% of the case, most of the cases, we never reach that speed of rotating field. The rotor is slightly shy of that speed. For that, we introduce a new concept that we call it sleep, and new parameters. But before that, let's remind. We said magnetic field revolve one in a two-pole machine for each cycle of the current. So in a two-pole machine, please take care, just for two-pole machine, the speed is omega s equal to 2pfs, and this f is frequency of the the stator supply voltage, also current, in fact, the same. So the omega s was the angular frequency of the current in the two poles machine. The angular speed, the rotational speed of the field, magnetic field, was also omega s, because in each cycle of that it revolves once. But in a more general case, we introduce something, we call it synchronous speed, and it is the rotational speed of the magnetic field. In a p-pole machine, in general, we talked about two poles machines. But in a more general case, in a p-pole machine, it will be equal to 2 over p omega s. If we have talked about that magnetic field in a more mathematical way, it was very easy to prove this. But now that we just leave it as a conceptual basic one, just please accept it from me that the formula for the rotational magnetic speed is 2 over p omega s. This one is in radian per second. If we are going to calculate it in round per meter or RPM, ns, we call it ns, will be equal to 120 fsp. If you accept that one, 2 over p omega s, deriving this one is easy. It doesn't need to just trust in me. You can find it with simple math. So, if it means that Fs is impacting the Ns, it depends on which system you have connected your AC machine. So, if you are connected to the 6 Hz system, like North America, for a two-pole machine, the speed will be 3600 RPM. For 4-pole will be 1800. For 6-pole 1200, and for 8-pole 900 RPM. And if you have a 10 poles, it will be 720. So the synchronous speed is something inherent to the machine. Once you built it, you cannot change it unless you change the frequency of the supply. Which one is not clear? Okay, let me write it in different color. So, is it clear now? But if you take very same machine from the North America and take it to the Europe and plug it to the system, they start to rotate at a different speed. In a 50 Hz system, the speed of two poles machine will be 1300 RPM, 4-pole will be 1500, 6-pole 1000, 8-pole 750, and 10 poles is 600. So it's very much function of the frequency of supply and the number of poles, which is determined at the time of building the machine. You cannot change it usually. And don't take a machine from here and simply plug it somewhere in Europe. There are more than just a frequency to that, lots of more standards issues. But as I said, we never reach this synchronous speed by the rotor. The rotor usually, in most of the cases, especially in slip rings motors, in cage motors, in the squirrel cage one, we are a bit shy of that speed. And then we introduce something that we call it a slip. We show it by S, and it's equal to synchronous speed minus shaft or rotor. They are very much the same. The shaft is connected to the rotor. Speed over synchronous speed. In a more mathematical language, S is equal to 2 over P omega S minus omega over 2 over P omega S, or if we want to mention it in RPM, is NS minus N over NS. Omega is shaft speed in radian per second, and N is shaft speed in RPM, and we already know the relation between them. Omega is almost equal to N over 9.55. So if I try to be more descriptive, slip is the difference between the synchronous speed which is the angular speed of the rotating field, and the shaft speed as a percent of the synchronous speed. Is very much the same as what we have above, but just in a more descriptive way. Any question up to now? Any question? Anyone is done writing? Okay. So we can also write it like this, that n, the shaft speed, is equal to 1 minus s ns, or omega, which this time is just in radian per second, last time was in RPM, it's 1 minus s 2 over p omega s. In case of a squirrel cage, that many times we just shorten as a cage machine or cage motor, the slip is small, typically between 0.01 and 0.06. It means that the shaft speed spins at a speed very close to that of the rotational field. So if S is between 0.01 and 0.06, sorry, it means here for an squirrel cage, this value is something between 94 to 0.99. See, N will be very close to NS. N is not a wide range, just between 0.94 to 0.99. That's why a squirrel cage can be almost considered as a constant speed. It's not exactly constant speed, but they are changed in a very tight band. So squirrel cage machines are inherently constant speed machines. Then no surprise that they are not very good for the wind generators. That wind speed is always changing and we want a variable speed from the generators. But this is not the case for the wound rotors. We will discuss this in a more mathematical way, and we show you and we will use it. But the difference here is that you can see a wound rotor here, wound rotor induction machine here. We can connect the slip rings. The slip rings are here. These are the 3 slip rings. We can connect them to external resistance in old time, Nowadays we connect them, there are cases that they connect them to some power electronic circuits, but from very old time there is one solution that we connect them to some external resistance shown there. These are external resistors, and through them we can control and we can find different S. So the point of a squirrel cage is very robust, it's very good, but we don't have that much control over them. If we need to change their speed very much, we have a problem. But for the wound, it's very simple. Even we just simply adding 3 resistors to the slip rings and we can control them. So here the shaft speed can be significantly varied by connecting external resistors to their slip rings. Everyone's okay here? Any question? Okay. Everyone done writing? One is writing. 2, 3. Okay, I think we can go to the next slide. Okay, example. A squirrel cage 5 horsepower induction motor excited by 60 Hz source has a full load speed at 1140 RPM. Calculate the number of poles. So what we have said previously said, okay, in a squirrel cage, we stay very close to the synchronous speed. And synchronous speeds for a 60 Hz system is very known to us. It's based on the number of the poles. So just we don't need the 50 Hz system here because we said we are interested in the 60 Hz. So we know for the 2 poles we have 1600, 3600, for 4 poles 1800, 6 poles 1200, and 8 poles 900. And we know that the speed stay very close to the synchronous speed, and closest one here is this one, 1200. So this is a 6-pole machine. So the shaft speed in a cage motor is slightly smaller than the synchronous speed. Thank bigger of motor and smaller, we will talk about this soon. The closest larger synchronous speed than 1140 RPM, which corresponds to a 6-pole machine, is 1200 RPM. So P is equal to 6 and NS is equal to 1200 RPM. Any question here? Any question? Everyone done writing? I think we can go to the next slide. It asks us the slip, rotor frequency, and rotor angular frequency. So S is very easy to calculate, equal to ns minus n over ns will be equal to 1200 minus 1140 over 1200. It will be equal to 0.05 or 5%. For the rotor frequency, Fr is equal to SFS. It's this formula we are going to use it. This is the frequency of the current and voltage inside the rotor. We induce some voltage and current inside the rotor. The frequency can be calculated like that. It is equal to 0.05 multiplied by 60 Hertz. It will be equal to 3 Hertz. The frequency of the voltage and current inside the rotor is 3 Hertz. Though it's not the best place, but here you can see why we cannot usually go to S to 0. Because the frequency becomes 0 and no AC voltage or current can be induced inside the rotor. So that's why S is usually a bit larger than 0 for the motors, especially cage motors. Rotor angular frequency omega r can be calculated at S omega s which is equal to 0.05 multiplied by 377 will be equal to 18.85 radian per second. Or alternatively, we could say omega r is equal to 2 pi fr, which is equal to 2 pi multiplied by 3 hertz will be equal very much the same value. So this one and this one. And just remember that this is the frequency of at which rotor current and induced voltage change. Any question here? Okay, the last part is very easy. It asks us the shaft speed and rated torque. So omega is equal to 140 over 9.55. It will be 119.37 radian per second. And we know that P is equal to T omega. So T will be equal to P over omega will be equal to, it's 5 horsepower, but bring it back to the watt and divide it by the speed in radian per second. So the T will be equal to 31.2 Newton meter. Nothing new here, in fact. Any question here? Everyone done? Okay. Let's talk a bit more about this sleep, different cases of this sleep, because in many cases when we talk about the induction motors, we usually talk in the language of the sleep instead of talking in anything else, and very much in many cases just give you the sleep. So it's very good to have an idea how this sleep is related to the speed. One is locked rotor. So in some cases, we may lock the rotor to does not move. One of the reasons we may want to do some tests, actually one of the famous tests for the induction machines are locked rotor tests, but also there are some other applications for the locking the rotors that's I'm not going to talk about them here, some kind of voltage regulation or those stuff, and they're not conventional too. But anyway, in this case, rotor is not rotating, is not revolving. So the speed will be, what will be the speed? What is the speed? It's not rotating. Zero. Thank you for listening. Okay, so this is the case for a standstill. So we is not just like rotor. For any standstill motors at the start of its moving, n is 0. In that case, s is equal to 1. A rotor that is speeding at synchronous speed, this time n is equal to ns. What will be the slip? Slip 0. A rotor is spinning or rotated at any speed faster than synchronous speed. In this case, n is larger than ns, so s will be lower than 0. And in fact, it's generator mode. When we are in the generator mode, it's happening. We are not going to talk about this very much in this course, but it's good to know. Everyone done writing? A rotor is spinning or rotated at any speed in opposite direction of the rotating magnetic field. In this case means n is smaller than 0 because it's in opposite direction. We show it with a negative sign. In that case, s will be greater than 1. But how such a thing can happen? A motor spinning at the opposite direction. In fact, it doesn't usually happen like this. We can change the direction of the magnetic field very easily. So consider on the system on the left that the 3 phases are connected. In this system, for example, it is magnetic field is rotating at the counterclockwise with the speed of ns. If I keep the third wire and swap the 2 upper phases like this, then the magnitude of the speed will be the same, but the direction will be the opposite. If we have talked mathematically about the rotating magnetic field in the air gap, it was very simple to prove this. But for now, you accept it from me. And in fact, will you do that in the power system? When we have a drive and we want to stop it very fast, one of the solutions is that just swap 2 of the phases. The direction of the magnetic field will change, and then motors start to decrease in the speed very rapidly. But the problem is that if we continue like that, when the speed reaches 0, it continues and then start to rotate at the opposite direction. So if you want to use it as a breaker, you should stop the supply when the speed is very close to 0 or 0. Otherwise, the motor starts rotating at the opposite direction. But it is used, in fact, in the industry as a way of braking. And that's why this mode is known as plugging or breaking. In next session, we talk about this mode in more detail. And let me also write about the direction of the rotating magnetic field. So the direction of the rotating magnetic field can be reversed by swapping two of the supply phases. Okay, are you done writing? No. Sorry. Okay. Done writing now? Done? Nice. So let me summarize what we discussed in last two slides. So when n was equal to 0, s was equal to 1, and we call this the stand still mode. When n was equal to ns, s was, as your friend said, 0, and then sometimes we call this free running, and you will see soon why. The torque, in fact, in this mode is 0. We cannot develop any torque, and we talk about it more later. When n is between 0 and ns, so s is between 0 and 1, we are in motor mode. When n is greater than ns, s will be less than 0, and we are in generator mode. And when n is less than 0, s will be greater than 1, and we are in braking mode. And in our braking mode in power system, in machines, electric machines, we usually try to return the power to the supply rather than wasting, like that happen in most of mechanical system with the braking and lengths. Okay. Let me go to the next slide. I think we are good with the principles, so let's start modeling the machines. That's the part that mathematics and all the questions usually comes out. So we said we have three phases, and these three phases are very similar to each other. So what we are usually doing, instead of make three models for each phases, we just use one model for one phase, and said, okay, the other phases just have 120 volts, 20 degrees different in angle, so the results are very similar, and we generalize the result and we use for them. So we usually go with the per phase model. And for the rest of these sessions, this one and the next one, for the induction machine, we use this per phase model. The model for the induction machines are very similar, in fact, in many aspects to the transformers, because the basics in some way is very similar. What we have done there, we had one windings and we have the magnetic system, the core, and we try to induce the voltage in the other winding. Very similar things happening in the induction machine. So it's no surprise that we see something very similar here. So here we have the source with the voltage of Vs, which is connected to the stator, and supply us the current of Is. Then because we have some winding, we will have a resistance here, Rs, because it's the stator. Then we have the inductance here. It is the leakage inductance that we have because of the leakage of the windings, the leakage of the magnetic flux in the windings of the stator, JXL, leakage of a stator, S. Then we need to magnetize the system, and this time we have an air gap, a considerable air gap. So a difference here is that we need a higher magnetizing current. So we will have JXM with the current of IM. And the voltage of this part, the voltage of air gap, we call it E1. And this part all together is the stator side at frequency Fs, and omega s is equal to 2 pi Fs. Then the energy goes through the air gap and induce the voltage inside the rotor windings, the rotor circuit. Again, if we have went through all the mathematics for the magnetic field, it was very simple to show that voltage here is SE1. And here we are at different frequency, at FR frequency. So again, because we have a winding, we will have some leakage, and the leakage is JSLR. So XLR is the reactance at the stator frequency. But here we are not at the frequency of Fs. We are at the frequency of Fr, and we said Fr is SFS. So instead of that, we still express XLR at the Fs frequency, but add the S there, this S, to bring it back to the Fr frequency. And then we have the current in the rotor, IR. Then, because of the windings or bars in the case of a squirrel cage, for sure they have some resistance. Let's call it RI for now. In case of wound rotor, we can add some external resistance. So this one, let me write this first. Here is rotor winding resistance. But as I said, in case of the wound rotor with the slip ring, we can connect some external resistance at the slip ring. Or external. This one is external resistance connected to the slip rings. There are 4 cage machines. So in case of cage machines, there are 0. And hold this part together. We call this R. Bless you. And here is a rotor side at frequency of FR equal to SFS, or omega R is equal to S omega S. Here will be the circuit of induction machine. Anyone done writing? Any question here? So for sake of your future reference, let's introduce this parameter that we have used here. S was the slip. In some references, you may see that they use the name of fractional slip. It's very much the same, just different naming. RS is a stator winding per phase resistance RR is, as we just discussed, is the aggregated or sum of the rotor winding per phase resistance, that we show it with RI. You can see it in the figure above. And the external resistance that might be connected to the slip rings in wound rotor machines, that we show it with our external. The external resistance is 0 for cage machines. Any question here? I think everything is straightforward. Okay. Everyone's done writing? Okay. Then we have XLR, sorry. XLR is 2 pi fs LLR is the rotor winding leakage reactance per phase for sure at the supply frequency. That's why we have to add the S before that, because it's rotating the frequencies FR, but we express as XLR at the FS. Supply frequency FS. LLR is corresponding leakage inductance. Very similar here for XLS is 2 pi fs LLS, the stator winding leakage reactance for sure per phase at the supply frequency Fs, and LLS is the corresponding leakage inductance. Okay. Everyone done here? Can I go to the next slide? Everyone done writing? Okay. Xm is 2 pi fslm is the machine magnetizing reactance per phase at the supply frequency Fs. Lm is the corresponding magnetizing inductance. Okay. The rest is very simple. Vs is a source, but take care of this, is a phase to neutral. It's very important to take care of this one. It may sometimes mislead you, especially in solving the questions. Voltage it is also the stator phase to neutral terminal voltage. Is a stator phase current. IR is rotor phase current. And IM is magnetizing phase current. The model is very much similar to the model of the transformers, but there are some differences if you pay more attention. First of all, you don't see any RC, the core losses. Does it mean that we don't have any core losses here? No. The point is that at very high speed, when n is very close to an s, so s or sleep is very small, as a result fr, the frequency of the rotor circuit is small, so the core losses will be small. But at that speed, at very high speeds, the mechanical losses, the friction and windage losses are high. At lower speeds, now S is higher, the frequency of the rotor is higher, then the core losses is higher. But the mechanical losses now is lower because we are working at lower speeds. So they found out the experience that in many cases, the sum of the core losses and mechanical losses remain relatively constant in induction machines. That's why they remove the RC here and add those losses to mechanical losses, said it's constant. It doesn't vary that much. It's one difference. Other than that, the circuit seems very similar to the circuits of the transformer, but the main difference is in the magnitude. So previously, in transformers, IM, magnetizing current, was from 1 to 5% of the rating current. But now here we have an A gap, and magnetizing A gap needs much more power, much more energy. So IM in induction machine can be from 30 to 50% of the rated current. The other difference is XLS, or the leakage of the state. Now we have an A gap, and also as I told you, they use usually distributed windings inside the state. So the leakage in induction machines is much higher than transformers. So though the circuits are very much similar, there are differences in the magnitudes that we can see. But the problem with, what is the main problem with this model, you think? The model that we just introduced. What do you think? What is the main problem with using this model? Any idea? Any educated guess? We have mentioned it. So what is the frequency for this stator? What was the frequency for this stator? It was Fs. What was the frequency for the rotor? Said it's Fr. Two circuits connected here, working at different frequencies. It's not something that we like. So the problem here, the problem of this circuit, when we talk about the problem, we talk about the problem of this circuit. It works at two different frequencies. This one is at Fs, this one is at Fr. So we need a better model. And in fact, we have a very simple solution. Said, okay, we know that IR is equal to SE1 over RR plus JSXLR. Okay, let's divide both numerator and denominator by S. It will become E1 over RR over S plus JXLR. We get rid of that S that was there because of the frequency. So we can have our new model and get rid of this transformer here. Here is VS, then here will be RS, no change, JXLS, here JXM, and here we will have IS, and the voltage here like before is E1, but by multiplying here is also E1, and now here will be JXLR. We get rid of that S, but the current is very much the same, but the change, the real change is here. We have RR over S, which is equal to RRI plus R external, remember, S. And let me emphasize once more that this one is for cage machine is 0. And all of this circuit, it's at Fs or omega s equal to 2 pi Fs. And we call this model T model. I think it's very obvious that why they call it T. Or in some references, you will see that they call it IEEE recommended model. And IEEE is International Organization of the Electrical Engineers. It's our mafia system that we have. So that's it all, I think, for today. Let's finish it here and we continue just from here the next week. Thank you.